so last time we talked about simulating one policy and then getting the value of another policy. And we showed how when it's possible. It's possible when for each state, the probability of one value occurring under the first policy divided by the probability of the other value occurring for this other policy is known, although we don't know the states and the transition probabilities and so on. Okay, so that's where we are. And what we're trying to do now is show that indeed we know how to calculate this ratio, although we don't know the probability, the transition probabilities, and we don't know anything about the environment other than that it's Markovian. Okay? So consider this path. Actually, you know, it continues, but we assume it's finite. So consider this path. The path starts from S0. You perform an action A0, and you get a reward from the environment R0, and then you get to state S1. Okay? And that continues, S1, A1, R1, S2, A2, R2, and so on, a finite numbers of time. Okay? Now, once this occurred, it has different probabilities for the first, if we choose to act according to the first policy or the second policy. So let's explicitly write what's the probability of this path occurring under the first policy and then under the second policy. Okay? So whether I'm in S0 or not, this is determined by the environment. It's not dependent to the policy. Not dependent on the policy, okay? So this is a P S0. And then the transition or the action that I'm taking depends on the policy. So say there's two possible actions, and with probability half I'm taking the first action or the second action. So this is a probability. So with probability half, I'm going to get to A0. Okay? It's clear at that point?
I'm going to get to S1.
To A0. From S, I'm going to take the action A0. Then the environment will get me to S1.
Oh, okay.
Okay, that's the probability I don't control and I don't know. Okay? But I don't care that I don't know them. I don't know it because it would cancel when I divide it. Okay?
Sure.
So this is the thing I'm controlling and I know. Everything I'm controlling and I know, then I know it, will not cancel. Everything that I don't know, when I divide it, will cancel. Okay? So let's keep going here. So the reward, the probability that I get a reward R0, given that I took the action A0, and I started from S0. Okay, that's some probability that I don't know. But it's determined by the environment. Same thing here. So that's the probability I get to S1, given I took the action A0, and I was in the state S0. Now when this same thing apply, but only changing this to the probability of the other policy. Now when I divide it, I get only the probabilities of the policies which I control, that I know them. Okay? So actually I know the value, this value. And therefore I can calculate the value of, I can estimate the value of the other policy, given the value of the current policy.
Given that you know the probability to take each action on each state.
Yeah, because that's what I determine. That's the definition of the policy. Okay, so say you have like a Markov chain here. And if you can take two actions, right? You have two states, and you can take two actions. This is action 1, and this is action 2. Okay? Now you could say that the probability here is half and half. That would be the first policy. And your second policy in S1 would be 1/3 and 2/3. Okay? So for each state, your policy is just a distribution of the action. Okay, and you make it, you flip your coin, so to speak, and you make your choice. Now during the simulation, you decide to just act according to this, and you collect the data, you sum up the rewards, and you know what the reward is for this. Okay? Now because we know this, we can also estimate the value of this policy. That's the trick. Okay?